Chapter 3, Vectors in Physics. We have a lot of quantities in physics that are vectors. We have a lot of quantities that are scalars. It is important to identify both of them, and it is important to work with vectors because most of the next few chapters we're dealing with quantities that are vectors. So it's important to, as I said, identify them, and it is important to be able to analyze them, something that we call in physics vector analysis. Okay, so let's take a look at the scalar quantities first. So scalars are quantities that are just a simple number with units. They are measurable, so you can measure them. Things like time, okay, things like speed, things like temperature, and so on. Mass, for example, I have it right there. All right, so these are scalars, meaning that if I give you just a number for them and a unit, I've given you enough information about them. You don't need to know their direction because they're not vectors quantities, okay? For example, time, 20 seconds. Speed, 5 meters per second. Temperature, 20 degrees Celsius, things like that, right? So now it's important to understand that speed is a scalar, but velocity is a vector. So if I'm talking about v, either v bar or v average or whatever it is, then that means that I am talking about a vector. Okay, it needs a magnitude, a number associated with it, but it also requires to have some sort of a direction. For example, with a velocity of 20 meters per second due north or south or east west. So you have to present some sort of information about the direction of a vector, okay? On the other hand, in one hand we had vectors, scalars, and then the other hand we have vectors. So these are the quantities that are required to have, as I said, magnitude and direction. For example, delta x, which was displacement. Okay, you need to know what direction the displacement happened. Okay, velocity is another vector. Acceleration is another vector. Force, F, is another vector. Okay, these are both required to have a magnitude, how big a displacement is, and some sort of a direction. Okay, when we're talking about direction, we have to have a coordinate system. Okay, so we have to have a coordinate system because direction needs along x direction, along y direction, for example, towards west, towards east, things like that. So you have to know your direction. And what we do, we present them by an arrow. Okay, for example, if I have an arrow, if I have displacement of 5 meters, and if I want to have the displacement of 10 meters, which is double of 5, if I want to show it with arrow, I have to somehow draw an arrow which is double the size of the previous one, something like this. Okay, with kind of the same direction. All right, so the length of an arrow indicates the magnitude. So obviously 10 is double of 5, so the magnitude of the arrow that I'm drawing should be double of the magnitude of, for this arrow. And the direction is indicated by the head of an arrow. So this is towards east, or to the right, right? And when we want to write a vector, it is important to put a little arrow on top, kind of saying that I understand this is the vector and we're communicating, we're all saying that it is a vector. Now, it might be a little bit difficult to keep track of it during an exam or homework. Sometimes even I might, write something that's a vector, but I forget to put an arrow on top of it. I have seen it from a lot of physics students not being able to, or not memorizing it to do it, not doing it pretty often. And that's cool, as long as you know that we have these quantities are vectors. And even if you forget to put the arrow on top, it's still okay, but it is important to do that. Okay, now vector example. So for example, I have a velocity of 4 meters per second, which is looking like this, going to northeast, 4 meters per second. Let's just call it v, okay? And I'm gonna put an arrow on top. And I have another vector, which is the magnitude of it is twice. So it is 2v. So 2 times v, 2 times 4 is 8. And it has the same direction, but the magnitude of it is double. So the arrow that I'm drawing here is double. That's 4, that's 8, okay? If I want to draw, for example, 12, then I have to have 3 times 4, okay? So let's say that this is 12. So I say 3 times v is 12 meters per second. So it's important to draw on a scale, okay? And be able to work with them. For example, I have a car here starting off from the center right there, okay, with some sort of a velocity, and it has moved 2 kilometers, okay? So delta x is 2 kilometers. Now, if I just give you it moved 2 kilometers, and the displacement was 2 kilometers, this will bring a question mark to your head. Like, in what direction did it move? Did it move towards east, west? Where did you go? Like, where is this car going to? So that's why we have provided another piece of information, 30 degrees, okay? So delta x and theta, or angle, being 30 degrees, okay? Meaning that I have given you the magnitude of 2 kilometers, I have given you the direction. Now I have provided you with enough information about this displacement, okay? If I had the same type of displacement of 2 kilometers for another car, but this time the angle was negative 30, okay? That means that this car has started the same point, but ended up negative 30 degrees. So kind of right there, all right? And this is the finish point. So if I am giving you, if the problem is asking you about the displacement, and you can, just by looking at the problem, you can tell that it is the vector analysis. It is important to care about and watch for the direction of these quantities, okay? Either the displacement, velocity, acceleration, force. Force is also another piece of information that requires a direction. For example, if you have a box, for example, okay, and we have a force being applied to this box, a force of 20 Newton, and we'll get to this later on in the next few chapters. So if I have a force applying to this, it is important to see where this force is applying to and how it's applying to. The magnitude is 20, but is it applying like this? Is this force being applied to this box like that? Okay. Is it being applied to this box like this? It is important to know what direction this force is and being applied to the box. Unit vectors. Very, very important. Very important. So I'm just going to put this in the box. It is a little bit confusing, but it has a very good application associated with it. So a vector with a magnitude of 1 that gives the direction, okay? Typically use unit vectors in x, y, or z direction. For example, in x direction, we have x hat as the unit vector along the x. In y direction, we have y hat as a unit vector along y. And in z direction, we have z hat as a unit vector along z. So sometimes we show these by I hat, j hat, and k hat. So for instead of x hat, so this is the same as x hat. So for along x, you either use x hat or I hat. Along y, you either use y hat or j hat. Along z, you either use z hat or k. I personally prefer ijk. If most of the physicists using ijk, but it's absolutely okay to use x hat, y hat, and z hat. These are two different forms, two different notations for one concept. So you can use either of them, and it's absolutely fine. I prefer ijk. Now, what does it mean when it comes to using these unit vectors? For example, I can say that delta x, or a displacement, was 5 along the x direction. Okay. Instead of writing it along the x direction, I can just say delta x was 5 I hat or 5x hat, right? This means the magnitude was 5 and it was along the x direction, okay? 5 times the unit vector along the direction. I can tell you that the magnitude of the displacement along y was 10 j hat, meaning the magnitude was 10 and it was along y direction, okay? So it's important to use them. It's very, very useful, and you'll see what I mean once we start to solving problems in this chapter. So let's take a look at this little example. So if two vectors are given such that a plus b equals 0, so we add them up and they add up to be 0. What can you say about the magnitude and direction of vectors a and b? A, same magnitude but can be in any direction. B, same magnitude but must be in the same direction. C, different magnitudes but must be in the same direction. And D, same magnitude but must be in the opposite direction. So if you want to think about this is, I have added up the two vectors, but they ended up being 0. So they have to be magnitude, their magnitude should be the same, but they should be into two different directions, the opposite directions, to cancel out, kind of like this. So let's say I have let's say that I have A here, okay, so that's A, and I have B like that. So that is A, and that is B. They are equal in size. Their magnitude are the same, but their direction are not. Their direction are opposite. That's why if you add them up, you will get 0. Okay, their magnitudes are the same. And when it comes to magnitude, if you want to show it, the way that we show it is this: A, and we put it in two parallel lines like that. Magnitude of A and magnitude of B are the same. Okay, they are the same, but they have the different and opposite direction. Okay, components of vectors, and this is the part that those I hat and j hat are coming to play. Okay, so a vector could be along x direction, a vector could be along y direction, and a vector could be in a direction to have some portion of it along x and some portion of it along y. So basically splitting vectors into pieces in the x direction and a piece in the y direction. Okay, so take a look at this. For example, I have the same. I have a coordinate system, just like what we have up there, but I want to draw one because I just like to draw, right? Okay, so I have x direction and y direction here. And I have a vector A, just want to call it A, all right? And that vector A has a portion or a projection along x direction, which I just call it A sub x. It's another vector, so I will put a bar on top, okay? Now, the same vector will have a projection along y direction, right? So it will be kind of like that. So A sub y. Okay. Now, if you're looking at this, I can easily move this A sub y or A of y, A along y direction. I can move this guy. Let's see if I can do it with this. Can I do that? No. Yeah. I can move it right there. All right. I can move this vector along y to here, and we'll get the same thing. So this vector r, has a projection along x direction, which we call it x here, and a projection along y direction, call it y here, okay? So remember, you can have y direction here, y portion of the vector here, or you can have it right there. They're both the same. They are parallel, they have the same direction, and they have the same magnitude, so you can just move it over there, okay? And that is the angle of 90 degrees. So we can split vectors, all right, along x and y. And this is something very, very useful. For example, I can, I have two vectors, for example, here. Let me draw x and y. I have two vectors. One is A and the other one is B. And the question is, if we add their portion along x direction, what are we going to get? So let's see. So I have this along x to be A sub x as a vector, and then I have b along x to be b sub x, all right? If you add them up along x, you'll get something like that, okay? So they have a projection. If you project vector A in x direction, you'll get this, a sub x. If you project b along x, you'll get b sub x. And you can add them up. You can do whatever you want with them. All right? Okay. So the vector components of vector A, are two perpendicular vectors, a sub x, and it's a vector, and a sub y, it's a vector again, that are parallel to x and y axis, all right? And if we add them, we'll get the same vector, original vector A. So in other words, this vector A here, all right, this vector A here has a projection along x direction, which is a sub x, and has a projection along y direction, which is a sub y. And as I said, I can just move this a sub y. I can move this projection along y to right there. So kind of having it like that, like a triangle, okay? A along x, a along y, and you can just add them. And if you add them up, you'll get the same vector A. And we'll talk about how to add up those explicitly in the next video. So that's the end of part 1. We'll start off with part 2 next.